Good evening. I'm Don Levy. I'm Vice President for Research and National Labs, and I'm very pleased to see this enormous crowd here, including a great number of repeat offenders, and I hope that those who are here for the first time become repeat offenders for future occasions. This is the 11th one of these joint speaker series that we've had, and the object of it is to bring together three institutions, the University of Chicago, Argonne National Lab, and Fermilab, just to meet people you wouldn't ordinarily meet during the ordinary course of your day, and to have fun and to see something interesting. Those who have been here before know that all of this has been done by Lisa LaValle, who is in my office. And each time she does one of these, you wonder how she's going to get better at the next one, and it always happens. This morning, I must confess, I caused Lisa to faint dead away when I pointed out to her that she was competing with the Blackhawks tonight. But as near as I can tell, we outdrew the Blackhawks. The only thing left for me to do is to introduce the moderator of tonight's program, my good friend and colleague, Sid Nagel. Sid is a very distinguished physicist at the University of Chicago in the James Franck Institute. He happens to have his office 2 doors down from my office, so we see a certain amount of each other. We also tend to work out in the gym at the same time as each other. And he is, I could go on for half an hour and give all his distinctions, and that would waste a lot of time, but he is a distinguished service professor at the University of Chicago. He's a member of the National Academy of Sciences. He won the Buckley Prize. Everything that goes good with a condensed matter physicist he has. His research is actually very interesting. He works in what is called disordered systems, and it's very fancy physics, but it frequently gets down to everyday things. So among other things, he's been known to study the stains that come off of coffee cups. You'll notice they have a particular pattern, and you never tried to figure out why. He tried to figure out why. He works with sand piles. He works with boxes of nuts. Why do the nuts segregate as they do? He works with dropping fluids. So he's done a lot of very important physics. He also does lots of other stuff. He's a noted photographer. If you come up to my office on the 6th floor, you'll note a lot of photographs, very striking, very artistic, and they're experiments from his lab, which he has taken. And we have them there for their artistic merit, not because the price is right, although the price is right. And as was pointed out in the video, he and his wife, who is also a very distinguished experimental physicist, Young-Ki Kim, are very interested in music and have salons weekly, more or less. So Sid is really a man for all seasons, and it's a pleasure to have him here tonight. I'll point out that the last guy who was described as a man for all seasons wound up having his head cut off in the end. So we hope better for you. But Sid, it's all yours.
Well, with that kind of introduction, I should get out of here quick. But this is really a spectacular crowd here tonight. And as Don said, I think we should really thank his office, the Office of Vice President for Research and National Labs, and especially Lisa LaValle, and also Sandra Marijan, who helped put this all together. So let's give them a hand. I can't see where they are, but well, they're there. Okay, there she is. Okay, and of course, there is no more appropriate place than Buddy Guy's Legends to hold this discussion about how how sound pervades our lives and influences our emotions. And I would like to thank the staff here, especially Randy Hyduk and his staff, for helping put this all together. And so let's give them a hand. So what is sound? Well, sound is vibration, and it pervades all our lives. We rejoice in the sound of a child's laughter. We are frightened by the sound of thunder. We are devastated by the sound of vibrations produced by earthquakes that shake our buildings into rubble. But vibrations could be more refined, and much of what we learn is communicated through sound and the feeling of vibrations from when we were very small. Music communicates complex and subtle emotions. Spoken words communicate complex and often esoteric thoughts. The analysis of sound is arguably the first great success of Western science. Pythagoras, living around 500 BC, related sound to geometry and to numbers. He thus related the phenomena occurring in the natural world around us to physical and mathematical principles. Following that lead, sound and music became a metaphor for the regularity of nature and even for the movement of the heavens. The connections between science, technology, and music continue to run very deep. The acoustics of a concert hall, the use of digital computers to create, compose, and analyze music, and the material science of constructing a fine instrument are just a few examples of the fruitful interplay between the science of vibrations and the art of music that goes on today. As I said, sound pervades all our lives, and as we shall see tonight, our thoughts as well, often in subtle and very non-obvious ways. We have 4 distinguished speakers tonight who come from very different areas of endeavor. We will see how sound has implications and is a tool for exploration in cosmology, in anthropology, biology, and of course in music. Each of our speakers will give a 10-minute overview of their work and how it relates to tonight's topic. After each presentation, we will take only a few minutes from a few questions from the audience before the next speaker comes up. But then after all 4 speakers have given their talks, we'll have all of them come up and you'll have a free-for-all where you can do whatever you want to them. I won't interfere. Okay, so with that, I want to first introduce our first speaker, Brad Benson, who is an associate scientist and Wilson Fellow at Fermilab and an assistant professor in astronomy and astrophysics at the University of Chicago. Over a series of trips, Brad has clocked more than a year at the South Pole Telescope Station in Antarctica, so that's cold. He does this, his work seeks to answer some of the biggest questions in cosmology, and he does this by simply listening to the sound of the universe. So we're going back to Pythagoras again. To hear more about that, please welcome Brad Benson to the stage.
So I'm going to talk about cosmic sound, in particular how we use this telescope, which is the South Pole Telescope, located at the geographic South Pole, to study the very early universe at a time shortly after the Big Bang, where we're literally trying to peer out so far that we're looking at the universe in a very different state, a state when the universe, before there were stars, before there were galaxies, and the universe was just literally just a fireball of hot gas, and how when you make observations of what the universe looked like then, you learn that the universe had a very regular harmonic pattern, which we can use to learn about the content and the evolution of the universe. Okay. So if you want to learn about the history of the universe, all you need to do is look up at the sky. Telescopes are like time machines just because light has a finite speed, so it takes time for light to get to us. So the sun is about 8 light minutes away. The nearest star, Alpha Centauri, is about 4 light years away. And so if you want to learn about the universe's history, all you have to do is make a deep observation of the sky. And we've done that in optical with the biggest, most powerful telescope we've made, which is the Hubble Space Telescope. And this is the so-called Hubble Deep Field, where they use the Hubble telescope to look at a small patch of sky for about 3 months to see what they would learn. So this image here is basically about angular size. If you stuck a pin through a piece of paper and held it at arm's length, this is all that you would see if you looked at that patch for about 3 months. So this patch was effectively empty, but when you do this deep exposure, all these objects pop out. And for a non-astronomer, what might surprise you is there are over 10,000 objects in this image, but only a handful of them are stars. There are over 10,000 galaxies, each galaxy having 100 billion stars in each galaxy. And we're really looking at some of the oldest galaxies ever imaged by humans. However, from the point of view of a person that's trying to learn about the very early universe, how did the universe begin, it's still a bit of a disappointment, this picture, because even as hard as we've tried, there's still basically black darkness between all the galaxies. We don't really see, we're not able to peer back to a period in the universe before there were stars, before there were galaxies. So the universe began with a Big Bang. There's a lot of evidence for that, and I'll talk about a little bit in this talk. But what does that mean? So if the universe began with a Big Bang, number one, it means the universe is expanding. As you look further out, things are moving faster away from you. And what that also means is, basically in the universe's past, the universe used to be much smaller, much denser, and also therefore much hotter. And so if you were to look out far enough and deep enough, you should be able to look back to a period when the universe was so dense that it was so hot that stars weren't forming, where the universe was just literally a fireball of hot gas, something that, basically roughly equivalent to the temperature of the surface of the sun. You see this fireball if you could peer back deep enough. And that's what we're trying to do with these observations. So basically this theory that there would be this glow to the sky, leftover light from the Big Bang, was confirmed in 1965. So this is the 50th anniversary of the discovery of this light left over from the Big Bang, which we call the cosmic microwave background, or CMB. So, and it was discovered serendipitously by two AT&T Bell Labs astronomers, Penzias and Wilson, who were just trying to calibrate their radio telescope in New Jersey, and discovered that the whole sky was literally aglow with microwave radiation. And so if your eyes were microwave sensitive, you would see this as well, that the sky was literally on fire with this light left over from the Big Bang. And just to give you some idea of how bright it would be, if you took a census of all the electromagnetic energy emitted over the entire history of the universe, over 90% of it would be still in the form of this light left over from the Big Bang. So it's literally has outshone the entire universe of all the stars that have ever been emitted or existed in the lifetime of the universe by over a factor of 10. So it's extremely bright. And that's part of the reason why they could find it sort of serendipitously. They didn't have to look very hard. And one of the common examples is that if you, in the old TV antenna, roughly 1% of the static in a TV antenna, if you go off station, is actually light left over from the Big Bang. Even a TV antenna is sensitive enough to see the light from the Big Bang. So that's one important fact. It's really bright, and it's not surprising in the sense that when it was emitted, the universe was about 400,000 years old. Literally, it was on fire on order of 4,000 degrees temperature. And so literally, it's the light emitted from just this fireball of the entire universe literally being on fire. And it's been traveling for 14 billion years to get to us and to be detected by Penzias Wilson and what we're trying to do measurements today. So we've been studying the CMB, this light from the Big Bang, for about 50 years. And one thing that's a bit surprising is that what we've learned is the best place to observe the CMB is the South Pole, and it's really just due to the unique conditions in the South Pole, Antarctica. And this is a picture of the South Pole. I mean, there's not much to see there. Here's our telescope. Here's the South Pole station and a lot of logistical support. And pretty close to the station, actually, is the actual geographic South Pole, the thing that the Earth rotates around. And you can also see here from the picture, it's entirely featureless, right? You're on a 2-mile thick ice sheet. So the bedrock is about 200 feet above sea level, and then literally there's 2 miles of ice above that. And that's where we have our telescopes and make our measurements. So 10,000 feet isn't so high, but at the same time, what really makes the South Pole unique is the other conditions. Number one, it's extremely dry. So in Antarctica, in winter, the coldest it gets is about minus 100 Fahrenheit, so very cold. And so when the air is that cold, it literally can't hold much water vapor. And much how a microwave oven works, water vapor absorbs microwaves, that water vapor heats up your food. Similarly, if the sky has water vapor in it, it absorbs microwaves from the sky. So the drier a place is, the better. And the South Pole is literally one of the driest places we know of on Earth. Number two, what's really important is the stable atmosphere. Because you're at the South Pole, when the sun rises, it rises for 6 months, and it spirals around you every day, slowly rising a little bit more every day, and then after a period of 3 months, starts spiraling down, and then sets for 6 months. So there's 6 months of night, or day, followed by 6 months of night. And so what that means for the atmosphere is it's extremely stable. Normally when the sun sets and rises, it stirs up the atmosphere and causes fluctuations, disturbances. The South Pole has really unique conditions to make the atmosphere really stable. So, one common question is, how do you get to the South Pole, right? So it's pretty inaccessible. There's only about 3 months a year where it's warm enough for planes to land. So we have to go there during the South Pole summer, where the temperatures are more on the order of minus 40 degrees rather than minus 100. And so when we want to install a new experiment, we have to get in there for those 3 months. So it's their summer, it's our winter. You first fly commercially to New Zealand. You get all your cold weather gear, the stuff that you need, parkas, snow pants to survive outside. And then you take military flights, first LC-17 flight to McMurdo, which is the biggest American base on the continent, right on the coast. Spend a few days in McMurdo trying to get training, and then take another 3-hour flight for about another 800 kilometers to the South Pole, the geographic South Pole, where there's a sign that lets you know where you are, at least. All right, so it's very important to get in there during the summer when planes can land. But then, of course, we want the best observations are when it's the coldest, when the air is the driest. So we leave, for our experiment, South Pole Telescope, 2 people behind to run the telescope during that 9-month winter. And there's about a station of about 40 people that are left behind to keep the station going during those winter months. And there's been people at the South Pole for nearly 60 years, actually, maintaining that base. So this is the project that I work on, the South Pole Telescope. It's a 10-millimeter wavelength telescope, really designed to make these microwave observations of this light left over from the Big Bang, the CMB. And it's the biggest telescope in the world that does these observations. So it's really unique. And it's been observing since 2007, so almost 8 years, making these deep observation maps of this microwave background, this light left over from the Big Bang. So what does it look like? So this is a sub-image of a map that the SPT makes. This is a 50 square degree patch. So for the scale, here's the moon, which is about ½ degree in scale. And so what you're seeing here, all these large scale fluctuations in the map, that's literally the fireball of gas in the early universe right after the Big Bang. So these are overdensities, slight overdensities in the universe, where the gas is about 1 part in 100,000 hotter than the other gas around in this primordial universe. And what's really important about this is these 1 part in 100,000 fluctuations, eventually, if you kind of fast forward 14 billion years, are going to turn into the galaxies, clusters of galaxies, all the structure in the universe where galaxies have formed, stars have formed, and where we live today. So depending on if you live in one of these overdensities, we'll tell if you live in an overdensity of galaxies today. Presumably, this part of the universe has this rich structure that we see around us as well, but it's going to take another 14 billion years for that light to get to us and actually see the universe in this patch of sky in its new, different state. Okay, let's go back. So the way to most usefully characterize the information is to take a power spectrum, much like you would for a stereo amplifier. And so this is an example of that, of just listening to different sounds, different animals. So if you listen and then divide this up into a frequency spectrum, different animals, different music, different instruments have different frequencies that they emit at, basically. And if you took a spectrum, you could actually learn a lot about what's making the noise just by the frequency of the sound that's being made. And similar, especially with musical instruments, there's always a tone and then overtones, harmonics, that you can measure and learn about what instrument is making that sound. And similarly, you can do the same thing with these maps of the microwave background and learn about what the content of the universe is, what's making all that structure. So if you take a power spectrum, an angular power spectrum of that map, this is what you would see. So this is the fluctuation power, the amplitude of the structure in that map is a function of angular scale. So this is much like the frequency spectrum that you saw with the sound in the previous graph. And what you see is there's this very regular harmonic structure. And these colored points are all measurements, actually. So there's this remarkable regular harmonic structure of a primary fundamental tone and then overtones that repeats out over the whole entire range of this map. Okay, and so what's causing this? So basically, in these slight overdensities, the evolution of the universe is really governed by 2 things. This expansion initiated during the Big Bang, and then gravity pulling things together. And so there's a biggest scale that you'll see in the map, which is basically equal to the sound speed in this primordial plasma in the very early universe times the age of the universe when that light was emitted. And so there's a biggest scale that's had time to collapse at this time where this light was emitted. And similarly, there's a sort of next smallest scale that's had time to collapse. As the gas collapses, the pressure of that gas increases, initiates a sound wave, and causes the gas then to expand. And then Similarly, there's another next smaller scale that's had time to expand and then collapse again. So you expect this sort of regular harmonic pattern just set by the sound speed in the early universe times the age of the universe. And then this scale is generated by these pressure waves in this primordial plasma. So when you look at these peaks, that's what this corresponds to. The biggest scale that's had time to collapse is the sort of the fundamental tone. And then there are harmonics that correspond to these resonances, these harmonics in this early universe corresponding to these next smaller scales that have had time to expand and collapse. And then one thing I didn't point out here is there's actually also a line over plotted all these measurements, which is our model fit. So it turns out we can fit these measurements with a relatively simple cosmological model with only 6 parameters that actually matches the measurements really well. And in addition, this model matches what we see around us today. Sort of later measurements of the evolution of the universe match very well these measurements, what we infer about the content and the evolution of the universe just from this harmonic structure that we see in this map from the light from the Big Bang. And one thing we found and discovered is that the universe is a very strange place. If you try to understand what the content of the universe is required to make that sort of regular harmonic structure, we learned that we don't really know that much about the content of the universe. Only about 4% of it is sort of so-called regular matter, atoms, things that are stars, planets, you and me, are regular matter. The rest of it seems to be 2 mysterious components called dark matter, which basically doesn't emit light but has gravity. And then an even stranger component called dark energy, which makes up about 70% of the universe, which is something that has an energy density but seems to be causing the expansion of the universe to accelerate in a very mysterious way. And so that's one of the great mysteries that cosmologists and astronomers are trying to learn about today is what's these components of the universe that we don't understand. In particular, what component of the universe could exist that causing this expansion to accelerate in this way that we can only explain with something like this dark energy. Okay, and thank you.
Okay. So we promised that there'd be time for questions, but we only have time for one question and a brief question. So is there a brief question?
That person back there?
Where I can't see it then.
So, what was the speed of sound in the ancient universe since it is density dependent?
So the speed of sound was basically roughly 1/3 the speed of light. Yeah, so it's pretty fast.
Cool. Well, that was a very quick answer to a very quick question, and so thank you very much.
Yeah, thank you.
So I would now like to introduce our second speaker, Michael Dietler, who's a professor of anthropology at the University of Chicago. Michael is an archaeologist and an ethnographer. For nearly 30 years, he has visited the south of France to study ancient Mediterranean France. And so you can either go to the South Pole or you can go to the south of France, and it's your choice, but I'm betting with him. His work also focuses on Celtic, European, and African cultures and includes ethnomusicology. A longtime fan of blues music and artists, Michael teaches a class on the Chicago blues. Tonight, he'll share some of his knowledge with us. Please join me in welcoming Michael Dietler.
Thanks very much. So can you hear me? Yeah. Good. I actually brought a text along tonight to impose some discipline on my notoriously undisciplined sense of time. Because I have 10 minutes to present what I have difficulty compressing into a 10-week course. So anyway, this is going to be highly simplified and very quick, but hopefully you'll get some sense of it. So my presentation tonight is about the history of Chicago blues, which is a highly appropriate place to do it here, I think, in this cathedral of the blues that is Buddy Guy's. And by the way, I hope you will come back to Buddy Guy's again, because there's a lot of great music that's played here every night of the week. So this is, in addition to an exploration of the history of the blues, also an attempt to illustrate a social science approach to sound. And more specifically, I want to illustrate the approach of a hybrid subfield that's called ethnomusicology. And this is also known as the anthropology of music. Basically, this approach focuses not only on the structure of music as a system of sounds, as music theory does, but more importantly on what people do with music and how they do it. In other words, we look at music as a culturally patterned social practice rather than a thing. And if one can use the analogy of language, we're not quite so interested as much in abstract systems of grammar and syntax as in speech acts and speech communities and things of that nature. So we study how people use certain kinds of sounds that we call music as a form of expression and a way of producing various kinds of effects, including provoking memory, emotion, communal identity, and action of various kinds. Now, the obvious corollary is that music is a social practice and therefore is constantly changing and must be understood in terms of the social history of which it is a part. Now, Chicago blues is actually a great case in point because it evolved originally from a form of music called Delta blues that originated in the last decades of the 19th century among African-American sharecroppers in the cotton country of Mississippi. That is the Delta in the middle of Mississippi. Now, to understand how and why this music changed from the early Delta practitioners, such as Charlie Patton or Robert Johnson, through the post-war Chicago blues of Muddy Waters and Howlin' Wolf, and the so-called West Side sound of Buddy Guy and Otis Rush, to the subsequent generation of urban-born musicians that are currently active now on the scene, one has to, I think, understand the processes by which it came to Chicago and the history of the African-American community here in Chicago. Now, in brief, and I should say very brief, to understand Chicago blues, one must understand the Great Migration that occurred over the first half of the 20th century, during which over 6 million African Americans left the rural South and resettled in northern cities. And this process occurred in 3 parallel streams. In the West, from Texas to California; in the East, from Georgia and the Carolinas to New York, Philadelphia, and other cities of the Northeast; and in the middle of the country, from Mississippi to Chicago, Detroit, and other Midwestern cities. And this is why Chicago is often jokingly referred to by some African Americans as Northern Mississippi. Now, each of these original regions had its own distinctive cultural patterns, including regionally distinctive patterns of blues music that developed there. And each of these blues forms were carried north by musicians who formed part of the Great Migration. Now, in the case of the Piedmont blues of the Southeast, this music eventually died out without giving rise to an urban successor. But both Delta and Texas blues were transformed by artists to conform to new urban circumstances and develop new styles out of this older material. Moreover, these musics subsequently stimulated the birth of a whole series of other new forms of music, such as rock and roll, rock, and blues rock. Now, the Delta blues were created around the 1890s as an expressive means of coping with the new form of de facto slavery that replaced the earlier system of legal slavery that was done away with by the Civil War. Now, this was a system of sharecropping in which poor tenant farmers were held in permanent debt, working on the plantations of white landowners. And it was coupled with a system of organized terror, discrimination, humiliation, and racial segregation known as Jim Crow that persisted until the 1960s, when the civil rights movement was finally able to force the federal government to enforce the freedoms that had been guaranteed by Lincoln's 14th Amendment 100 years earlier. Now, to be clear, the blues is not African music. It is African American music, a brilliant, original creation that emerged out of the most brutal conditions of racist domination and became the most influential music of the 20th century. It has influenced virtually every form of current form of popular music that is known, and it has been just an enormously influential music. So people moved north to escape the terror and humiliation of the Jim Crow South, and also for the much greater economic opportunities of factory jobs in industrial cities such as Chicago, which was often referred to as the Promised Land. Now, when they got here, it turned out to be not quite the paradise that they had imagined originally. But their lives were vastly better in many ways. African Americans here could vote, they could go to school, they could earn good money, and not fear being lynched for looking the wrong way at white people. But they did still find plenty of racism and discrimination. And it was this that forced them to live in the confined area of the so-called Black Belt of the South Side, which later became known as Bronzeville. Now, this did have one advantage in that all of the African American social classes were living together in one community, and they were able to form almost a parallel city within Chicago that was a vibrant cultural center and a source of optimistic pride as well. However, by the 1960s, the industrial base of Chicago was in decline, and housing restrictions had been overturned, resulting in the migration of the middle class to the suburbs, rising unemployment among the former working class, and the gradual decline of life on the South Side. Now, these are important forces to bear in mind in understanding the evolution of the blues, which went through several changes once it reached Chicago. In the Delta, this music was performed by a single individual accompanying himself on guitar or harmonica. And there were many itinerant musicians who roamed the countryside playing at juke joints and house parties. Now, once the music migrated north, the musicians began to play together in bars, forming bands of several musicians playing together and electrifying the instruments to make themselves heard. But the music wasn't simply amplified. They used the electronics to produce new effects that turned the music into a much tougher and more assertive force that reflected their new environment and the new identities that were emerging there. And the music changed again in the 1960s to become even grittier and tougher, reflecting the new reality of the decline in the fortunes of the South Side. Now, this is also reflected in a study of the lyrics and other aspects of the music that I don't really have time to go into here, but I thought it best simply to close by giving you a few examples that will, I hope, give you a sense of the transformations that I'm talking about. So I'm going to give you 4 musical examples. I have 5 here, but I'm going to cut one out because of time. And I'm going to start with Delta, Robert Johnson playing a song that's become a very famous part of the repertoire of Chicago blues. And a lot of those Delta songs still form the core of the repertoire of the Chicago blues, but there has been a lot added to them as well. So I'm going to give you Robert Johnson playing one of his original recordings, and then a Chicago version of that about 25 years later, which shows you what has been done to the music here. And you get this sense of this really thumping, driving backbeat to the music and what electrification and playing with bands has done. I'll then give you a sample from the 1960s to show you the so-called West Side sound, in which you get the development of the single string style of guitar playing, and you get this really searing style of solo guitar and a really kind of soaring vocals that intermingle with each other. This is a style that has become really classic, of which Buddy Guy was one of the original developers. And then finally, I'll give you a sample of some of the born in the urban north generation and show you what the music is like today. And this is a continuing development of the tradition of the blues. The blues is still very much alive and kicking. So anyway, these are the samples. So first, the Robert Johnson sound from the Delta.
I'm gonna get up in the morning, I believe I'll dust my broom. I'm gonna get up in the morning, I believe I'll dust my broom. That's when the black man you've been loving, good friend can get my room.
And now the same song, Chicago style.
I'm getting up soon
So that's the classic post-war Chicago sound, and now I'm going to give you the 1960s so-called West Side guitar sound. This is Buddy Guy playing.
I sit and cry, oh, and I sing the blues. I sit and cry, and I sing the blues. Oh, there's no one to call me sweet thing. And my heart is filled with pain.
Anyway, it kills me to cut these things off, but alas, my 10 minutes. So now I'm going to give you a sound from the first generation that was actually born in the urban north. John Primer, the guitarist you saw in the original film, actually was one of the last of the ones to come up from Mississippi. But all of the rest of the musicians you see here, you can see in many of the clubs in Chicago, including here at Buddy Guy's, they were all born in the north, many in Chicago. So this is the current sound of what that tradition of development is in the blues here.
Gone and let me hear the cry. No, I love her. No, she my desire. 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 Came on the morning about 4:30. Found that note lying on my floor. Gone away and leave you. You just don't know. Heard some bad talk. Something that you say. Something that you say. Something that you say. Come on back, baby. Honey, please don't go. Well, I love you. You never know. You never know. You never know. You never know. My kind of baby. You know it's so. I have to tell you. You know it ain't no joke. You know it ain't no joke.
So, alas, that's all we have time for. Anyway, as I mentioned, there's often a lot of talk about, the last of the blues and keeping the blues alive. But let me assure you, the blues is very much alive, and you can come down to Buddy Guy's any day of the week and see it here on view. So anyway, with that, I'll open it up to questions, if we have some time left.
Time for one question.
Robert Johnson, what happened to him?
He died very young. Well, there's a lot of discussion about that. It's under very mysterious circumstances. Some people claimed he was poisoned by the husband of his girlfriend, who also happened to be the owner of the juke joint in which he was playing. There are also lots of legends about him selling his soul to the devil to get his talent, and that the devil came to collect his soul and so forth. Nobody quite knows the real story, but he did die very early down in Mississippi after playing at a juke joint.
So he never came up to,
No, he was recorded in the South, and there were only 2 recording sessions of him. They were both done in hotels down in the South.
thank you.
Yeah.
Okay.
That's it. Thank you.
Let's thank Michael again. Okay, our third speaker tonight is another change in pace. It's Peter Larson, who is a computational biologist at Argonne National Laboratory. Before joining Argonne, he worked on protein engineering for the creation of novel enzyme activities for use in industrial applications and in microarrays for cancer diagnostics. At Argonne, Peter uses machine learning and artificial intelligence methods to address the problem of big data in science to study microbial communities and the relationships with human health. Peter has created a new form of science and sound called microbial bebop. Please join me in welcoming Peter.
So I work at Argonne Biosciences. The most important thing you need to know about life on Earth is the vast majority of it is, in fact, invisible. It was the 17th century. Early microscopes actually discovered these strange little animals, and they discovered them actually pretty much everywhere they looked. It took us until the 21st century when we had enough science, we had the molecular techniques, we had the computational techniques to start understanding what these little animals are actually doing on Earth. We now know most of the biomass on Earth is bacterial, so they're the biggest contribution to life. They contribute to every biogeochemical cycle on Earth, so our lives are completely dependent upon this invisible ecosystem. Even now, we can only see these things indirectly. So they don't grow in a lab. We can't go out into the wild and use a microscope and see these communities in action. So we have to look at them indirectly. One of those ways to look at them indirectly is computational biology. My job is to make this invisible world visible. This is an example. It combines a Earth system climate model with thousands and thousands of individual biological observations taken from all over the planet. We use that data to build an artificial neural network. This predicts the relative abundance of many species of bacteria everywhere. Turns out one of the best ways to make the invisible world visible is to make it audible. So we made an algorithm, microbial bebop. This is a method for sonifying big data, turning large amounts of data into something that can be heard as opposed to a graph or a figure that is meant to be looked at. I'm not a musician. So I approach music the same way I approach complex systems. I look for patterns that can be described in a mathematical way to reproduce these patterns in a systems model. So very briefly, this is the math part. This is the algorithm to generate microbial bebop, starting with data. Each of these rows is a data. Each of these columns is a single observation. Each of these columns is a kind of data. In real data, there might be hundreds of rows and thousands of columns. Normalize that data to a given dynamic range of integer values. Map those integer values to notes and chords. This way, we can convert the data directly into music, where every measure of this music is one biological observation. And we can play this example here. Listening to the chords that is given to us by the data, listening to the melody. And when we play them together, ooh. Okay, so you heard that dissonance. That dissonance is in the data, but we can do something with that computationally. We can rectify the melody to the chords to bring that melody so that it's in harmony with the chords. This does two things. Makes the music sound a little better, and It means that what we're seeing or we're hearing in this music is one kind of data's relationship to another kind of data. Had we generated the chords from a different set, that melody would be a different melody. This, for example, actually is almost 10 years of observations taken in the Western English Channel. These are bacteria that are normally found in very low abundance. Occasionally they spike to high abundance. The data identifies that two of the abiotic conditions of the water are the most predictive for causing these blooms. We can use that scientific observation, generate a music-like composition. So that's kind of cool. What do we do with it? I mean, what meaning can we draw from this? The obvious, easy application is education and scientific outreach. One of my favorite examples, a university in Stellenbosch, South Africa, actually reached out to us. We worked together to compose some compositions that derived from human microbiome, gut bacteria data. And then they took that music and taught it to a grade school choir. And they got to not only hear about the microbial communities, but they sung about them. That's kind of cool. For my interest, what I want to know is, can we use these tools as a serious computational tool? The two ways to think about big data, supercomputers versus, the human brain. This is a radically unfair comparison. Computers are stupid. They use megawatts of electricity. They use millions of gallons of water. They're only good at doing what they're told. Brains, on the other hand, use about as much power as the light bulb that comes on in your refrigerator. And every single one of them comes preloaded with pattern matching algorithms that have been optimized by millions of years of evolution. These are really good tools. One example of someone who's actually exploiting this is a program, Foldits. This is a gamification of protein structures. Using this tool, they capitalize on people's inherent intuition about objects in 3 dimensions. They find the optimal folding patterns for proteins. They have used this to design protein functions. Foldit can solve questions in days that would take a modern supercomputer years to do. So these tools can be used to solve scientific questions. Could music be used the same way? We have an intuition for 3-dimensional space. Longfellow and modern neurobiologists both agree music is, in fact, a universal language. Playing music is a skill. Listening to music is something we're born with. Listening to music is something that's definingly human. They can go to cultures that have never heard Western music. On the first hearing, they can tell is the intent sad, happy, sacred. Complete amateurs can listen to a song. If they know the song, they identify that song from a single note. Musical experts can be even more fine-tuned. A musical expert can identify the difference between a composition that was improvised and a composition that is a copy of that improvisation. So yes, the human brain has the intellectual capacity to use this for data analysis. So how much music is there? This is the universe. Music's bigger. Using the software that I have, I can generate a 8-note melody comprised of an octave and a half, different lengths, interspersed with rests of different lengths. I can very easily generate a unique 8-note melody for every star in the Milky Way. If I add instrumentation, change instrumentation, I can make an 8-note melody for every star in the universe and have data left over. This is good because these are bacteria that are actually living in the ocean. There are more bacteria on planet Earth than there are stars in the universe. This is a big search space. So music is actually a tool that has a search space almost big enough to fit life on Earth. So we have the 3 things that we need. Human beings have the capacity to detect very subtle patterns in music. Music is huge. We can generate a lot of data, make a lot of music. So one can really easily imagine a gamification of music and use it to crowdsource honest-to-goodness data applications. How do you look at big data? So when it comes down to supercomputers versus brain, obviously this was a joke. It's not one or the other. It's one and the other. These are two systems that have a lot to tell each other about analysis of big data. And the mechanism that could link these two systems is music. This one here is actually gut microbiome data over a period of time. So this is somebody who is in a period of good health during the course of this experiment. This is one of the songs that we generated for that group in South Africa. Do appreciate your attention. I'd be happy to take questions in the time we have left.
Okay, question over there.
Yes, could you please give this demonstration to the Department of Education?
I would be happy. I'm a terrible ham. Give me a stage. I'll talk to anybody you want. There was something over here.
Is the melody unique? Is it just one melody that you generate?
The melody is unique for a specific interpretation of the data set. So for example, we have 10 years of data collected from the English Channel. They collected bacterial samples, I think on a roughly weekly basis. They have an automated buoy that collects data about the water conditions on a daily basis. So that's thousands and thousands and thousands of data points. There are, I'm just going to shoot the moon and say an infinite number of ways you can combine that data. Every combination could be a unique melody.
You went from 3 digits to integers. It seems like you lost a lot of precision. Is that a problem?
That is part of the decision-making process for converting the data into music. Specifically, if you want to talk about how we do that, we do not seem to need a lot of individual values. We do always log base 2 transform the data because life lives at log scales and you do not get a good linear transformation of bacterial abundances unless you did a logarithmic transformation. As far as losing data for analysis, we have yet to actually use this approach to do hardcore data analysis. Right now it's been a scientific outreach education. Whether or not there is an optimal number of notes that is best for the data, we don't know. I do know if you go more than an octave and a half, it starts sounding really lousy. Thank you.
If you collect data from bacteria that are genetically related, closely related, and those that are not related, do they harmonize better when they are related than when they are not?
That's a very interesting question. For example, if we're thinking about that one example where we're looking at low abundance bacteria, one of those bacteria was Vibrio nales. One of the exciting things, well, exciting. One of the things about Vibrio nales is blooms of it are toxic. Not every Vibrio nales species is going to cause a toxic bloom. So that would actually be a really cool one to generate because you'd have a lot of things staying very stable with the toxic variants blooming under certain conditions. So the answer is, the short answer is yes, the long answer is probably.
So I guess I wanted to get my neck cut off, as Don said I would. And so if I ask, well, what have you learned from this? So you could sing the song to me, and I would say, oh, that's a nice song, or the tune, or whatever. But what I guess I would like to know is at the end, well, I'd like that even crisper, what is the take-home message aside from this song? And I guess I haven't quite.
No, that's an excellent question. And this was not, there's no Department of Energy that had asked me to, would you please generate music from bacteria. This was, my job is to think of interesting ways to analyze data. This was a way to approach the main advantage to me, thinking about complex data sets in new ways helps me to understand better approaches to data. I very much doubt I'm going to come up with a musical composition that's going to change my understanding of microbial ecology. The exercise of doing this has already done so. The other thing is, this was for kind of, I thought was more or less goofing around. This has found an audience which has utterly surprised me, but it suggests to me that there is a desire for understanding these systems, that people really actually want to know what's going on. They want to know, and this, what I have learned is people actually care about these kinds of questions, and that this is a very good tool for introducing this science to people who would otherwise have a steeper learning curve to talk about bacterial ecology.
Okay, well, with that, let's. Okay, so I guess this is our last speaker is coming up, and so I'd now like to introduce Augusta Reed Thomas, who's a university professor of composition at the University of Chicago. Augusta has won acclaim for dramatic, spontaneous quality of her work and her masterful use of instrumental color. Her many awards include recognition from the John Simon Guggenheim Foundation, the Siemens Foundation, and the National Endowment for the Arts. Colors of Love, a Chanticleer album featuring 2 of her compositions, received a Grammy-award in 2000. Her double concerto, Astral Canticle, was a finalist for the 2007 Pulitzer Prize in Music. Tonight, Augusta will discuss her composition, Helix Spirals, and how it relates to tonight's topic. Please welcome Augusta.
Good evening, ladies and gentlemen. I am so honored to be part of this occasion, and I thoroughly enjoyed the presentations of my colleagues. And I just wanted to say that I'm incredibly honored to be a member of this faculty. I feel so privileged for that. Tonight I'm going to be sharing some examples of maps and sketches of my work. And I'd like to speak about this work, Helix Spirals, which was commissioned by Gene Gilman in celebration of the Mendelssohn-Stahl DNA replication discovery of 1958. It's a string quartet, and it's in 3 movements. And this was premiered just a few weeks ago at Harvard University. This is a picture of Gene and Matthew Mendelssohn, and the Parker String Quartet and myself after a rehearsal a few weeks ago. So when Jean approached me, she said, clearly genetics is genetics and music is music. And we were thinking about how to bring together concepts from different conceptual domains. We agreed that if one were to take a data set, such as a DNA sequence, and assign to it a specific pitch or a specific harmony, you might result in something interesting, but it probably wouldn't be a well-sculpted composition of music that is working dramatically across 23 minutes. So this is slightly different from the sonification that Peter was just speaking about. I've written many works that relate to nature topics, stars and moons and galaxies and suns, many pieces along this line, A Circle Around the Sun, Absolute Ocean, Oriel, Earth Echoes, Resounding Earth, Silent Moon, Sun Threads, and so forth. This is a map of a piece of mine, Prisms of Light, and another light-related piece, Oriel. Some of you may remember that President Zimmer invited me to make a new piece for the opening of the Mansueto Library. And I was very honored by that invitation, and I made a piece for 2 violins entitled Double Helix. And I'd like to just play 45 seconds from this composition. I'll stop it there. So turning to DNA replication, thanks to the Messelson-Stahl discovery, we know that it reproduces in a semi-conservative manner where the double helix is unwound and each strand acts as a template for the next strand. So thinking about how I could compose a piece of music for Gene that in a way celebrated DNA and also its replication process. So what I decided to do is have the first movement, loci, be made, specific locations, be made up of short sounds, little dots as it were, as if they were flickering locations, and to have those dots coalesce into lines, which became the lines of the helix spiral, and then progress throughout the three movements over here to the third movement, spirals life force, which takes the same lines and treats them in a very contrapuntal and lyrical manner. I'd like to play for you a little bit from the first movement, loci memory palace, and this is quite quiet, this example. Lots of different kinds of sounds for string quartet. Playing with the wood of the bow. So in the next movement, let's see, I tried to do musically the way that DNA replicates. So what I did is I made the A chain of music, as it were, and then the B chain, and then A plus B, the helix, then A plus its new complementary strand Y, and B plus its new complementary strand Z. So this musically goes in this order. You have the A and then the B and then so on and so forth. What we have time to do tonight is just listen to the A strand. And sorry about that. But this is a very brilliant crowd, so I know you'll sort that. And I just wanted to say this piece of Kandinsky reminds me a lot of my own work. Transforming and connecting, taking something and looking at it from different perspectives, having things progress. Also, take one simple object and see how far you can move with it. And of course, nature is the great teacher about transformation and connections, and for me, about music composition. So here's the first A strand. It's heard first in the violin. This line goes on for 1 minute and 15 seconds. I'm going to jump to the next one. There we go. So now we're going to have A plus B, but you haven't heard B yet. And here it is. So you can hear them interlocking. So this is, in a way, the helix. Next, I'd like to play you A with Y. And in this case, the main line is played by the cello in a lower register, and the lagging strand is in the violin too. And so on and so forth. At the end of this movement, I decided to have the helix come back in the entire string quartet, and it sounds like this. The third movement is very lyrical, melodic, extremely contrapuntal. The lines are woven across the whole movement. I will just conclude with a few last thoughts. I've always been interested in the gestalt of putting together a composition, the notion that you can't separate color from pitch, you can't separate density from balance, or harmonic rhythm from flux. It's a little bit like doing a three-dimensional crossword puzzle, where when you put one new note in, or one new harmony, or one new color, the entire object has to relate in all kinds of dimensions. This is maps of 3 very recent works. That's my cello concerto from the Boston Symphony, and a piece called Celine, which was just premiered in New York several weeks ago. It's a messy map. And this is my most recent orchestral piece called Eos, which was premiered about 10 weeks ago, and the European premiere was just this past weekend. I wanted to just say one thing about next steps, which is interesting vis-a-vis Peter's presentation. An organization called the Sounds of Science has approached me for a commission for me to make a piece about protein folding, of all things. So I'm really looking forward to doing that. And thank you very much. I did bring a CD of the whole Helix Spirals. If anyone would like to hear it, you're most welcome to take one. Thank you. Do you want to do some questions?
So let's have a couple of questions for Augusta, and then we'll bring everyone up for free-for-all of questions.
Hi, what initially inspired you to compose music to represent the DNA structures? I don't know if you just said it very briefly. Was it because it's so in tune with nature, or just were you commissioned to do it? I'm just curious.
Oh, yeah, forgive me if I wasn't clear. I am very inspired by nature, the macro and the micro. And I feel if you were to look at all of my titles, so many of them are pointing to the natural world. Jean Gilman, who is the wife of Matthew Messelson, wanted to celebrate the Messelson stall DNA replication discovery with a piece of music. And so she asked me if I would imagine something going into the realm of metaphor and make a piece that would celebrate DNA and the way that DNA replicates, but also to make it a music composition. Thank you.
So, as I understand it, DNA is made out of 4 bases.
Yes.
Which would imply that you can make all those compositions out of 4 notes. If you use more than 4 notes, then it's not DNA. Thank you.
Right. That's what I was saying. If we want to be very specifically taking C, G, A, and T and adapting each of those to a certain pitch, or just using only those 4 pitches, one could make something. But I don't think it would be a sculpted piece of music composition that works dramatically, emotionally, musically, harmonically, contrapuntally, and all those things about music that I love. And so I jumped into the realm of metaphor. And otherwise, one is just making a sonification of some data field. And then in which case, you could pick any pitch to assign to anything, or you could pitch any harmony to assign to anything, and you end up with something. But it's a different project.
Okay, so can I have all of us thank Augusta again?
Thank you.
And now I'd like to bring all of the 4 speakers onto the podium to get grilled. Okay, so now we have time for all the questions that we didn't have right after the talks. And so let's start off here.
Professor Dietler, I had I had a visceral reaction to hearing recordings of the blues, and that caused me to ask a question, or to wonder about a question, and then I got an answer to the question. I thought, well, okay, does a serious ethnomusicologist tap his feet? And then later on, I saw you tapping your feet. I wondered if you'd be an objective scholar, distancing yourself from the music. And could you talk about the ethnomusicologist and the music in that regard?
Yeah, that's a very good question. Actually, I was trying to resist tapping my foot earlier on, but it sort of eventually broke out. It's like the John Lee Hooker song. He's got the boogie in him, and it's got to come out. No, I don't pretend to be a completely disinterested scholar of the blues. I came at it first as a blues fan, a lover of the music, and it was the blues that drew me in to try and explore the history and the culture that lay behind it, rather than just thinking as an ethnomusicologist, what project could I embark upon? So it's sort of the other way around. It was the subject itself which drew me into it. And one tries to be, well, as an anthropologist, one tries to sort of, what anthropologists do basically is they try to understand other cultures from the inside out. So you have this technique that's called participant observation, where you go and live with people, you learn to speak the language, you learn the way they see the world. And the idea is that by doing that, you can understand the way in which the culture as a whole works. And so this is basically what we try to do with music as well, to really sort of understand music not just as a system of sounds, or to appreciate it. I mean, you can appreciate music that you don't know anything about, but you're appreciating it for very ethnocentric reasons, because it corresponds to your own aesthetic dispositions. But it's something different to actually understand it from the inside. It's like learning a language. You can like French, the sound of French, very much without understanding a word of it. But you get a very different appreciation for it when you actually learn how to speak French. And so part of the idea is to learn to speak blues. And of course, one never becomes quite as good as the natives who really know it from the inside, who grow up speaking this language. But the point of anthropology is to really arrive at that kind of understanding. So, yeah.
But is one implication of your question that you shouldn't love what you study?
How does a scholar relate to the thing that the scholar is trying to study? He gave a very good answer.
My question is, the four of you have approached music and sound in a very different way. Hearing these different ways, has it inspired you to go back to your research or your work in a different way?
For me, absolutely. That was the reason I was really excited to come here tonight, is I know what I do. I really wanted to hear these other speakers. One of the big motivations for me to be here tonight was to hear these talks, to understand how to approach the universe in multiple ways. Again, that's my biggest motivation is, how do you think about patterns in the universe? How do you think about patterns in life? That's what I was here for, and I really think that's what I got.
Okay, I think we got another one here. Okay.
Yeah, I just want to say that I think this was a very cleverly designed panel, so thank you, Lisa and the team. So a question maybe for each of you briefly is where do you see your sound or music as the subject of your research or a tool for your research? And I think I heard different answer. Just curious if you could comment on that. If you're actually using that music or sound as a tool for the research or as the content of your research.
Start on the end.
Okay, I can begin. For me, I would say it's both. It is the music itself that I'm interested in, but music as a part of social life. So I'm very interested in the people behind the music as well. I don't think you have to choose one or the other. I mean, you could do that very easily, but for me, it's both of the things at the same time.
For me, it's definitely a tool. I'm not a musician. I didn't go into this expecting I was going to create works of great lasting beauty or even musical significance. but it was an attempt to visualize in a very different way the things that I want to see. So for me, it was definitely a tool. I have no illusions that I've created great music, but I had a blast approaching my data from a different way.
Yeah, when I first heard your question, the first thing that ran through my mind is it's actually my life. I mean, I think about sound every day. I compose music every day for literally my whole life. I've been playing music my entire life since I was a tiny child. And sculpting sounds and imagining sonic adventures and building forms and trying to be very concise and all these things, working those things out, it feels very, very close to, I can't separate my life from my work.
Yeah, I would resonate with that answer too, because it's kind of a tool in that we try to analyze the data to understand these harmonics, and that's the way we actually analyze the data to try to learn about the universe. But at the same time, it's also a very personal reaction of taking those measurements, seeing those measurements, looking at the data and seeing how beautiful it is. You're trying to ask these very personal human questions about the universe, what's it made of, how it's evolving, and a lot of times even making the measurements, going to the South Pole, seeing the data come in, there's a lot of human aspect of where you're really excited at a personal level, and you get that excitement when you're down there talking to all the other people doing this research too.
But particularly for you, Brad, I mean, it seemed to me in your talk you talked about two ways in which sound came into it.
Right.
One was that you played something from what you looked at the spectrum and you made that into sound.
Right.
And so that was using it as a tool. But then what was it all about was, I think what you told us was that structure was originally caused by sound.
Right.
So in that sense, it really was, you used it in two different ways. One was as a tool to look at the sound that originally created the universe structure the way it is.
Right, yeah, sound was ultimately the thing responsible for the evolution of the universe as it exists today, and you can see it in a really sort of clean example of that in the structure that you see in this microwave background.
One more here, Sid. If I understand this, okay. If I understand this whole business, everything starts from zero, is that correct? And that it's been answered with the Big Bang. Now the question is, how does the music start? What's the first sound? When a baby's born, you hear sound immediately, otherwise it's not alive. And so the question I have is, how does one start from zero and get where the hell we're at now?
I think that question's for me.
You're first in line.
Yeah, I mean, so I think one common thing that people ask is, how old is the universe? How big is the universe? And in some ways, in a lot of ways, we still don't really know. Like we can ask the question of how old is the universe as we know it, and it appeared to start. The universe as we know it appeared to start in this Big Bang 14 billion years ago. But that's not to say that the universe didn't exist for another 14 billion years before that, another 100 billion years, or an infinite before that. So, we try to ask questions which we can answer with measurements, and then there's some sort of even bigger and broader questions that it's hard for us just to experimentally answer and make measurements. So, I don't know that the universe began with a zero, actually. Yeah. It would have been very loud.
But it was in vacuum, so you couldn't hear it.
Yeah, that's right.
I have a question here.
Oh.
Hey, so I was thinking about the as a scientist, the beauty that I see whenever I figure out something for the first time, or when we as a group figure out something for the first time, and the beauty of linking one idea to another in a novel way. And I was wondering if one of you would like to speak to, I don't mean to suggest that there is such a thing as sound versus such a thing as music, but the point perhaps to you at which a collection of sounds turns into music. This is obviously a very very open to interpretation.
I mean, my thinking about music always starts from like a neurobiological. Music is a beautiful accident of the way humans are built. I think almost more than any other trait, I think music may be a defining human trait. I mean, there are examples of other kinds of cognitive abilities and other things. Music is unique. We're the apex of all the cool things that we do up here is teaching us to hear music. Music doesn't exist outside of here. There is no music. It doesn't exist. There was no initial music until it's here. It either starts here, it ends here. But until it's here, there is no music. So what's the difference between sound and music? Music's here. Sound is waves that just happen to bounce on our eardrum sometimes.
Can I jump in?
Oh, please.
Yeah. I would say that music's greatest quality is its capacity for change, transformation, and renewal. So I wouldn't want to say, okay, this is music, that's not music, because the minute you do that, then it becomes music. There's lots of different kinds of music. There's great music that of all colors and stripes and kinds. So one has to be careful. But I do feel that something becomes music when it is in some way organized and not just a field of amorphous objects that lasts 3 hours. Although there are some new pieces that sound like that. But when things get organized, and sometimes they get extremely organized, like Johann Sebastian Bach or Mozart or Beethoven or Ravel or Debussy, where you have the sense that every single 16th note has been addressed from absolutely every angle. The form is beautiful, the structure is incredible, the emotional content is vivid, the humanity is rich, it's something unique, a new perspective from that particular composer. Then I start to feel that we can, with great confidence, call that music. Again, keeping in mind there's a huge variety.
So there's something that people talk about, found art. Is there no such thing as found music?
Well, you get into the realm of beauty in the eye of the beholder. I mean, where do we hear patterns? Where do we hear organization? We might hear a piece that sounds like complete chaos, and somebody will say, well, I loved the second movement because I started to hear the way that things collided in different proportions or something. And somebody else will say, well, it just sounded like a jumbled mess. But on the other hand, somebody is perceiving that. So it's complicated.
One other thing I would say is that the way in which we define music is actually very culturally specific. Different cultures define it in different ways. And some cultures actually don't have a word for what we would call music. Some cultures, for example, don't distinguish dance and music. They're just one thing, in the way that some people don't differentiate between wet and cold. It's the same term for them. And every culture has something that produces the kinds of effects that we associate with music. But where they draw the boundaries of what is and what isn't music, or the way in which they classify it, is very different. So which is one of the reasons why we try to understand what other people think of as music, and then understand the aesthetics of it that they bring to the performance that they have.
I had a quick question. So I was struck by something that Peter said about instead of visualizing data to audiolize it. And I thought, one of the great breakthroughs of visual data of the Cartesian plane is you can instantly apprehend data in an instant. You can see it. And then when you listen to something, it obviously takes time, right? And you can't have a piece of music that doesn't take time to listen to, right? Or even sound. So I just wondered if any of you wanted to kind of comment on that. I mean, time played a role in each of your presentations. The history of the universe, the history of this movement from the South. Well, I just wondered if there's something inherent about music and sound that is tied to some temporality.
Yeah, I'll go after you.
My experience with big data. So I work with experiments that generate terabytes of data. The vast majority of it is crap. There is not a tool for visualizing a terabyte of data. That's just, we don't have that ability. We can't get that much information into a form. which is why I think a far more complex kind of translating complicated things into a complicated things for which we're designed to understand is a good idea. So yeah, there's time involved, but I'm working in a realm where a simple visualization I don't think is achievable.
Yeah, and I would say I find the work Peter's doing really fascinating and extremely useful and rich and important. In terms of the actual sound of something that has been sonified, if it ends up sounding like a random cliche chord progression, for a musician, it's less helpful to understand the data in a certain way. So I think the more specific the sonification becomes and granulated, the more interesting and the more one can get from it, rather than just sort of A minor goes to C major and then we have an extra G sharp or something. I mean, for someone who's done music their whole life, it can start to sound very, very, very generic, and I don't mean any offense at all, but no, it's just important because I think it is interesting, but sound, I guess what I'm saying is sound is so loaded and so precise. I mean, if you play one note tonight, I won't forget it. And if you play two, I'll remember them like forever. I mean, it's just very, very, very precise. And the relationships and the velocity of the sound, the density, the dynamic. Just doing something with dynamics alone, if you had just one pitch and you just did dynamics, you could tell a lot about data. So there's lots of different parameters of music that can come into sonification that can make it even more rich for those folks who have studied music their whole life.
Sid, we had one question here. Right here.
Back in your back. So thank you, first of all, for a wonderful evening, most entertaining and stimulating. I study biological rhythms, and the evening is all about rhythms and sound. And I have a question of pure curiosity, and maybe some of you in the audience might have an opinion about it. I find that, and I've kind of done some informal polls about it, my taste for music varies a lot across the time of day. What I want to hear in the morning as I wake up is not what I like to hear in the evening. And I was wondering whether there's any neurobiological or other evidence for that kind of behavior, and whether, for example, my dear colleague Augusta has a different take on her composing work as she gets up in the morning and as the day winds down.
Oh, thank you. Well, I listen to lots of different kinds of music. I listen to an enormous amount of jazz, as you might have picked up from the Helix Spirals, and I listen to music probably 6 to 8 hours a day, and I'm writing music all day. So there's lots of sounds flying around, and I think for my own body clock, I get up very, very early. I usually am writing by 4 in the morning. And so there's a certain intensity of getting up and doing that. And I guess as the day goes on, the body clock does change. I'm not sure if I'm answering your question particularly, but I definitely feel that, after a long day of work, and you want to come home and have a really nice glass of wine or something, there's certain music I wouldn't want to hear, and then and likewise, first thing in the morning, I probably wouldn't want to hear. So I think you're absolutely right. Same question.
Well, I mean, I like to, oftentimes when I'm in the lab, I really like listening to a lot of energetic music, just to kind of keep me going, especially with mundane lab-related tasks. I always do actually, at the South Pole in particular, when we're working, we play music constantly when we're working down there.
Hello. I have a question. Very nice presentation. And some cultures have, as you say, times of the day, like Indian classical music, divided into ragas, and each part of every 3 hours, a different type of music is played. Now, taking it down to the molecular level, how does that correlate movement, subatomic movements? And some cultures, they talk about universal vibration. How does that correlate with personal preference of this is the type of music I want to listen to this part of the day? Has there been any research in that area? And many people have used music as a healing. So how does that correlate with what we're talking about?
In my brief research into the area, I do know that, so I've read a lot of papers where they do a lot of MRIs of the brain when you're listening to music. Music affects, if I'm standing absolutely still, music causes the parts of my brain light up that incorporates movement. There's very ancient parts of my brain that light up when I hear music that's associated with emotion. Is there physics behind it? I don't know. If you ask me, I'm a biologist, so I think in terms of evolution. I think that we are evolved to enjoy sharing emotions. I think we're evolved to enjoy communications. I think we're evolved to enjoy synchronized moving in synchronization with our fellows. I think music trips all of those things, and it short circuits our survival. Everything about our survival, it short circuits and goes straight to the happy part. So I think when you're talking about what is music, music is the key that goes to our most ancient selves and lights it up. All millions of years of striving to survive is distilled in music, and that's what we hear.
We have time for just one more question, and so because after this question and the answer, you get to have dessert, and then this thing is over. But what's very nice about this is that you're all welcome to stay and hear the music that's coming after, starting at 9 o'clock, and the
9:30
is the Michael Charles Band is scheduled to perform tonight, and so you're all welcome to stick around for that. But one more question.
I have one question here.
Bringing it back on the MASH show a little bit, I'm fascinated by this idea of, and it's following up on a couple of questions ago, this idea of representing data as sound, because when we visualize data, sometimes we have an idea of what we're going to look for. Sometimes we just display things and patterns jump out at us. My question is, when you convert these data to sound, do you have in your mind an idea what you might discover by doing this? Or do you hope you're going to sit back and a pattern will emerge that gives you some deeper insight?
I have not generated a sufficient number of pieces with sufficient intent to suggest that this is a way of making new knowledge. I allow that this is a goal. I think that this is a fruitful area to search. I am certainly not there. And I'm going to say I'm very shy about talking to music right now because, like I said, I am not a musician, so I'm speaking I'm a guest in somebody else's space when I'm talking about music. But I think that I have not done so. I think that the capacity to do it is there.
Can I just add one thought? Because I really think it's fascinating what Peter's doing. And the one thing that we should just keep in mind is that music has easily 100 parameters. We're talking about the slight timbral shifts or tessitura or intensity of crescendo or whatever it might be. So if one does sonify certain data fields, it could become really, really rich to the point where you actually hear, let's say, this 2-minute sound field, and you can actually start to understand things. If we don't use enough parameters, it may be not ever able to tell us enough. I mean, I don't know, I've never done it, but it's just a thought.
This is what needs to be done. Actual grown-up musicians who have who know music and they know music and can speak music and can understand music and can teach meaningful things about music. I have no idea what you just said. So I mean, so there's no.
Sorry about that.
No. But that's what I'm saying is, I mean, I am completely blind to a field of human endeavor that, like I said, I'm messing around with, but don't know.
But I think it's really important. I mean, and there's some people in the music department, some of our PhD students have been sonifying data. And so it's something that the two departments can continue to work on. And people have really been starting to investigate this in a great way, I think. Yeah.
Okay, well, with that, I think this is a perfect end to the discussion tonight. I want to thank Don Levy's office, the Office of the Vice President for Research and National Labs, and especially Lisa Lavallee, wherever she is. I also want to thank the management and the staff of Buddy Guy's Legends, who have let us use their space in such a historic place to hold such a conversation. And with that, I hope you will all have dessert and stick around. And you can ask all the questions you didn't get a chance to ask because they'll be here. Thank you.